In today's lessons, we are going to be evaluating the uncertainty of contaminated soils based on the 10 conditional Gaussian simulations that we created at the previous video tutorial. To do that one, we are going to create new R scripts to be integrated in QGIS that are going to automate the entire process. We want to automate the entire process because in that way we are going to save a lot of hours in our projects. Also, we are going to see how to do the same process manually using the scripts that comes by default in QGIS. The goal is to compare the automation with the manual process. At the end, we are going to be working with Algebra of maps in order to extract the information that we need from each simulation to evaluate the uncertainty of the contaminated soils. The best part is this lesson is totally for free, is totally open. Anyone can have access and watch all the video tutorial. Join our YouTube community today by subscribing to our channel and hitting that bell icon for instant updates. Don't forget to show your appreciation by leaving a like and leaving a comment to engage with our content. Hello and welcome back to the Conditional Gaussian Simulation course. My name is Marcel and I'm the main instructor of this course. This is the lesson 5 and today we are going to be evaluating the uncertainty of contaminated soils. And the question is, what is the likelihood that this plot of land exhibits contaminated soils? Let's start. Before we begin, I would like to introduce what we accomplished in the previous lessons, with the aim of providing you with some context related to this project. Here we are in Netherlands. This one is the perimeter of the area of investigation, and today we are going to be working with the Meuse River dataset. This dataset is pretty popular because it was used for a lot of geostatistical projects, as anyone can access to this one totally for free. This dataset wants to explain the relation between the river Meuse, is this river over here, with the presence of contaminated soils at the flood areas. As you can see, this dataset has different parameters. We have the X and Y coordinates. We have several heavy metals. We have also the elevation, the distance to the river, the organic materia, the flow frequency, the type of soil. We have different parameters. But today we are going to be focused on the zinc concentration that is in ppm. In the first lesson of this course, what we did is the exploratory data analysis of the Meuse River dataset. We get a data distribution that it was pretty skewness. And then we transform the data in order to have a perfect Gaussian distribution. The technique that we was using to do the transformation, it was the Gaussian anamorphosis. In the second lesson, we was working with the simple kriging. First, what we did, it was the structural analysis or variography analysis. Then we created the grid for the interpolation, the grid for all this area of investigation. At the end, we perform the estimation using the simple kriging. Then we created these maps. This first map is associated with the Gaussian anamorphosis values. Then we created the variance map, also again associated with the Gaussian anamorphosis values. That's the transform values. At the end, we reverse the Gaussian anamorphosis in order to have the values in the original scale. These values are the zinc concentration in ppm. In the third lesson, we was analyzing the simple kriging model. And what we saw is that the values estimated using the simple kriging model doesn't replicate the statistics of the original dataset, and also doesn't replicate the spatial structure of the original dataset. As a result of this, the semivariance of the estimated values are smaller than the semivariance of the original dataset. Then we said that the simple kriging and also ordinary kriging provides models that are pretty smooth, and because of that, they are not pretty realistic. In the previous lesson, that it was the lesson 4, we was working with the conditional Gaussian simulation, and we executed our first simulations. Also, we saw how the simulations replicate the statistics and also the spatial structure of the original dataset, and we created several maps. First, we created the simulations based on the Gaussian anamorphosis values. It was 10 simulations, and also we reversed these simulations to the original scale. In this case, is with the values for the zinc concentration in parts per million, ppm. You have to understand that each of these simulations represents a potential real scenario. And these simulations is the ones that we are going to use today to evaluate the uncertainty of the contaminated soils. Then let's start to create some new scripts that are going to be used to manipulate raster files. Because as we know, these simulations, the file is a raster one because we have pixels. It's not a vectorial one. Then let's go to create the first script. In this case, what I'm going to show you is step by step how you can create scripts based on R to be integrated in QGIS. The first script is going to be very simple, but that's the way it works, right? We start for a very simple script, then we start to manipulate this script to make that one more complex. The first one is going to be how to load a raster file in QGIS using an R script. Then this one is the name. Then I'm going to cut this one. I'm going to remove these 2 lines. And I'm going to save in the default folder, okay? Then I paste the name over here and save. Then this script is going to create a group that is going to be raster conditional Gaussian simulation. Let me make this one bigger. And that's how indicate over here with 2 pounds. This one is going to be the things that we are going to see in the interface. We are going to create a slot to load the file and also a slot to save the file. Then the library that we are going to use is the raster. This library is to manipulate raster files. Then first, what we are going to do is to create a script that loads a raster. That is pretty simple, right? Then the name of the file is going to be loaded raster, and the script is just raster. And inside the raster, we put the path where we save that raster file, is this path over here. Then we can close this one here because we save already. Now we can go to R, and now we have a new group. That is a raster conditional Gaussian simulation. That's the group that we created. And here we have the script number 1, load raster. Then if we double click, we are going to see the interface for this script. And also if we click right in our mouse, we can edit the script. And here we have the information that we was seeing before, right? The group, as I said, is this one. And we indicate it with 2 pounds, and also here 2 pounds and 2 pounds for the interface, right? That we have in QGIS. Then now we can select here a raster that we want to load in QGIS. Then we can select any rasters that we created previously. We go to the simulation folder. We can go to the simple kriging. We can go to the rasters. And we can load, for example, the map prediction original, then open, and we can run. And as you can see, this script loaded this raster file, is this one over here. And as you can see here is saying loaded raster. That's the name that we put here at the script. If you open this one, edit the script, loaded raster, that's the name that we put to this object. And it's this one over here. Now we can remove this one here. And also we have the option to save this raster that we want to load with a different name. Then we can select a folder here, save file. We can select here the folder that I have for this new lesson that is evaluating uncertainty. And here we can put, for example, number 1. Then we can run, save, and we can run the script now. And now this raster is going to be saved in that folder with the name that we assignated. You see, raster number 1, and if we go to the folder, you are going to see that is saved over here. Now we can remove this one here first. Remove. Okay. And we can remove also in the folder. This script by itself, it's not really useful because it is not worth it to create a script to load a raster file. But it's useful for us because it's going to be the foundation, the base for the next script. Then we can close this one here and let's go to see the script number 2, create new script. And I'm going to paste what I did already. Let's go to make this one bigger. With this second script, what we are going to do is reclassify a raster. It means that we are going to take one of these raster files and we are going to modify the value of the pixel according to a specific rule. Then let's go to the script again. And this script is going to be called as number 2, reclassify raster. Then we can cut here, we can remove these 2 rows and save in the default folder, paste and save. Then here we are going to add this script to the same group that is called as raster for conditional Gaussian simulation. We are going to have a slot to load the original raster as we did in the previous script. And also we are going to add this new slot that is going to be the guideline level. That's the level of concentration that we are going to use to classify the pixels. Then we are going to be talking about this parameter later. And also we are going to create a slot to save the reclassified raster. And that's the slot, right? This one is for the interface for QGIS, and each of these slots has 2 bounds to indicate that one. Then we are going to use the same library as before, the raster one. We are going to use the same script that we was using at the previous script to load the raster with this script and with this path. Remember that this path is the path that we add over here. And now we have a new thing. In this case, is the reclassifying the raster. Then we are going to create an object that is going to have this name, and we are going to use this script, the script reclassify. Then here we are going to add the loaded raster, is this raster over here, and we are going to create a matrix with 2 different values. One value is going to go from -infinite to the guide level. Remember, the guide level is specified over here. It's going to be specified in a slot. And the other value in the matrix is going to be from the guide level to the infinite. Then here we have 2 values. One goes from the -infinite to the guide level, and the other one goes to the guide level to the infinite. And I want to assign different values. For all the values that goes from -infinite to the guide level is going to be 0. the pixel is going to have a value of 0. And for all the values that goes from the guide level to the infinite, the pixels are going to have a value of 1. Let's put an example. For example, let's go to imagine that the guide level is 1000. Then how it works in R. The value located at the left, in this case is this one, is the one is taking the 1000. It means that here all the values goes from minus infinite to 1000. And the value situated at the right has values bigger than 1000 to the infinite. Okay, the value at the left is the one who is taking the 1000, the guide level. And the value situated at the right is for values bigger than 1000. Then the last thing is this one. This is just to save the new raster file, because we are going to reclassify the pixels and then we are going to have a new raster. And this script is to save that raster, and it's going to be saved with this name. What object? This object. What is this object? This object over here. Now let's see how this script works. Then we can close here, go to R, raster for conditional Gaussian simulation, and now we have the script number 2. Double click to open. Then here the file that we are going to load is the simulation number 9 for the original scale. Then if we select this layer and click this option over here, we can check the values of the pixel. If you click in any pixel, you are going to have the value over here. As you can see, every time I press in a different pixel, the value is changing. Then we are going to reclassify these rasters in order to have two different values, 0 and 1. Then we can load that raster here. That is the number 9 for the original scale, this one over here. Then open, and here for the guide level, what we are going to add is 1000 as an example. 1000 and one more 0, and then we can run this script. And as you can see, if we move this one here, we have now a new raster file that is called reclassified raster, and has 0 and 1, just two values. Then again, if we take this tool over here and we select any pixel, you are going to see the values of the pixels. Here is 0, 0 for the white part. As you can see, now it's changing to 1. 0, black part, 1, white part. All the white pixels are indicating that the concentration of zinc is higher than 1000. And all the black pixels are indicating that the concentration is 1000 or below. 1000 for a zinc concentration is really high. Now I'm going to show you a guideline for groundwater and soil remediations in the province of Alberta in Canada. But be aware that each country and even each province or city, they can have their own regulations about the contaminated soils, and they are going to have different values for the guideline. In this case, our reference is Alberta Tier 1 Soil Remediation Guidelines. Here we have the type of soil that could be fine or coarse. In this case, there is no influence according to the type of sediment, because for both of them, it is the same guideline. Then we have the land use. We have natural areas, agricultural, residential parkland, commercial and industrial. And also here the zinc concentration in part per millions, that is milligrams per kilogram. Then for natural areas, the maximum could be 250. The same for agricultural and the same for residential. But for commercial and industrial, the maximum value is 410. Any value that is above this guideline needs to have a plan for a remediation in order to reduce the concentration of zinc to the guideline. In this case, we are assuming that the concentration of zinc that is above of the guideline is because of anthropogenic activity. If the situation is different because we have high concentrations of zinc because of natural occurrence, no remediation plan has to be activated, but we have to demonstrate that the concentrations above the high limit is something natural in that area. Then, taking in consideration these values and checking the Muse River data set, we can check now the attribute table. Here you can see the values for the zinc concentration in milligram per kilogram. And as you can see, there are a lot of values that are higher than 1000, even almost close to 2000. And these values are really, really, really high. And when we have a soil that has values too high, the soil can be declared as a contaminated soil. And when we have a piece of land that is declared as a contaminated soils, that piece of land has a very low value because it's contaminated and cannot be residential, cannot be agricultural, cannot be industrial. You cannot do any activity in that soil because this soil is contaminated. Well, this topic is not part of this course, could be part of a different course related with risk analysis for contaminated soils or something like that. Then let's go back to the script that we was creating. Then also here, if you want, you can save the new raster that we created with the reclassification of the pixels. Then just press this option, put a name, save, and then you are going to save this new raster in the folder that you want. Then we can close this one here. And now I want to show you how you can do the same using the scripts that comes by default in QGIS. Then we can close this one here, and here we can search for reclassify. Reclassify by table. Then double click to open. Here we can select the file that we want to reclassify. Is the same as before, simulation number 9 for original scale, open. In this case, also can be selected from the rasters loaded in the panel. Then here we have to create the matrix. Then we have to add 2 rows. In the first row, we are going to add the minimum value from 0 to 1000. And I want a value of 0. And here goes from 1000 to, for example, 10,000. We know there is no 10,000, but we want to add a big number here just to include all the values from 1000 to higher, right? And in this case, the value of the pixel is going to be 1, then OK. And here we have to go to advanced parameters and make sure we select the proper option. In this case, what we want is this option over here. And this one is OK. Then now we can run the script. Now we have the script loaded over here and is using this one over here. Then we can compare the results that we get using this script that it comes by default in QGIS with the script that we created. This one is the raster that has been loaded temporarily, and it comes from that script. Then if we take this one out, we can see that both rasters, the one that we created with the one that is created with the QGIS script, they are having the same results. We can take this one out. You can see this one and this one are totally the same. Now we can remove these 2 rasters. Okay, and also remove this one over here. And let's go to move on the next script. Then create a new script and paste what I did already. With this script, what we are going to do is the same as we did with the script number 2. Let me show you here. Our raster conditional Gaussian simulation, we are going to do the same that we did with this script, but for multiple rasters. Now we are going to create a script that we can load all these simulations in once and then run the script to do the reclassification for all of them at the same time. We don't have that script on QGIS. That's the way that we can automate the process. Then let's go to see the script. Is this one over here. Then that one is going to be saved with this name, reclassify multiple rasters, number 3. Then we can cut this one here, cut, remove these 2 rows here, save in the folder that it comes by default, paste and save. What we have here, we have the name of the group, we have all these slots to load the raster files, then we have the slot to put the guide level, and also we have all these slots to save the new reclassify rasters. Then here we are using again the library raster, and in this case we are going to create a list with the location of all the original raster files. It's the raster files that we are going to load here in these slots. Then we are going to create a function to load and reclassify raster by raster. That is going to be all this function over here. Then we are going to take the process raster, that is going to be a new object. This object is going to have a function where we are going to include all this list, that is the file path. That's this one that we put here. Then we are going to load all the rasters using this script and using the list that we created. And then we are going to reclassify all of them using the script reclassify. And then we are going to add different names for each of these processes. At the end, we are going to get a rasters that is going to be with this name, reclassify rasters, and it's going to be the end of this function. Then we are going to process each raster and save them in a list with this script over here, and then assign the rasters to the output variables with these scripts over here. These ones allow us to save the scripts in these slots over here. Then we can close this one here and run that script. That is going to be the number 3. Then go here, number 3, open, and now we can load all the simulations here. From the 1 to 10 is going to be these simulations over here with the original scale. Then we are going to start from the number 1. Now I'm going to pass the video faster. For the guide level, I'm going to add again 1000. This is just an example, right? You can add any guide level that you want. And I'm not going to save the files. I'm going to leave that one as a temporary one. Then we can run this script. Now what I have is the 10 simulations that has been reclassified. We have in total 10 new different rasters with the values from 0 to 1 for each of these simulations. As you can see over here, we can close this one. As you see now, each raster is different because it has different values for the pixels, and the reclassification is going to be different for each new raster. This one is the last one. Now we are going to plus all the layers. That is the algebra of maps. We have 10 reclassify simulations where we establish the guide value as 1000, and now we are going to plus all these layers. It means, for example, that if we have this pixel and this pixel is bigger than 1000 in all the layers, it means when we plus all the layers and we create a new one, that pixel are going to have a value of 10. If that pixel has a value of 10, it means that for all the simulations, that pixel has a value bigger than 1000. Then with the final layer, that is going to be the summation of all the layers, we can see what percentage each pixel has of having a value bigger than 1000. If that could be 100%, that could be 90%, that could be 80%, right? And that's what we are going to do now with the raster calculator. First, we are going to do with the raster calculator, but later I'm going to show you a script that can automate all the process. But first, let me show you with the raster calculator. Then, so a raster calculator, and here what we want is to plus all these layers. In total, there are 10 layers. Then if one pixel has a value of 1 for each layer, at the end, we are going to have a value of 10 that represents 100%. Then what we're going to do is click on the layer, plus, next layer, plus. This one is the manual way that we can do that one. But I'm going to show you an R script to automate all the process. But first, let me show you how it works manually. Then this one. 2 more layers. This one is going to be the last one. And now we can save this new layer that is going to be the summation of all these layers. Then click here. Select a folder where you want to save that one. In my case, it's going to be this folder, raster, and I'm going to save that one as a summation. Rasters. Then save, and now we can run this script. Also, we can select here the reference coordinate systems. That is the same as this one, 28992. This one over here, okay, and okay. And this one is the summation, the summation of all the layers. This one is the final raster. Then this one can be also classified with different colors. Then go to Properties, Single Band Pseudo Color. Here we can choose Equal Interval, and it's going to be 11. 11 because we have one that is 0. Because if we have a pixel that in all the layers has a value of 0, in the final raster is going to have a value of 0. Because this raster, as you can see, goes from 0 to 10. Then let's go to select a different ramp. For example, something that it's like this. Let me see. Okay, but let me change this color for something red. Okay. And even for the 0, we can make this one as a transparent. Okay. And apply. And okay. Now, if we take all the layers out, and we add here the satellite imagery, and this one is the final result. Then for the red colors, it means that we have a probability of 100% of having a value bigger than 1000. For the transparency, where we don't have any color, even we can add the perimeter here. When we don't have any color, it means that we have a 0% of probability of having a value bigger than 1000. Then if we compare the results that we get with the simulations with the simple kriging for the original scale, for the simple kriging for the scene concentration in ppm, you can see that this final raster is pretty similar to the simple kriging. The simple kriging, we have the highest values over here, and we have the same for the simulation. You can see we have the highest values over here, the highest values over here, and the highest values over here. And here there are some values that they are having a probability around 10% of having a value. We have to select this one here. You can see one value of 2. 2, it means that 2 layers has 1. It means 20%. Then in this way, we evaluate the uncertainty of the contaminated soils. Let me take the simple kriging out. Because here what we can see is what is the probability of having a value higher than 1000 in each pixel. And this is based in 10 simulations. Maybe 10 simulations is quite poor, but you can do the same process with 100 simulations. Then maybe you are going to have a more realistic value. Then as you can see, for example, if we select this pixel over here, we have a value of 1 indicating that we have a 10% of probability in this area to have a concentration higher than 1000. But for example, here, the probability is 80% in this pixel over here. And in this pixel over here is 100%. It means that we are 100% sure that in this area we have a concentration of zinc that is bigger than 1000. And this is based in 10 simulations. But if you add more simulations, and remember that each simulation represents a potential real scenario, then the results that you are going to get are even more realistic. Now, let's go to see the last script that are going to automate the entire process. Is this script over here, and we are going to save this script as number 4, reclassify multiple rasters and sum. Then let's go to cut this one here, remove these 2 lines, and save here, paste, and save. And for this script, we have the same as the number 3, but here we added this one. With this one, we can calculate the sum of all reclassified rasters. That's the script that we are using. But for the rest of the things, is the same as the other raster. But also here, the output raster is just one file, it's just one raster. At the number 3, it was 10 because we put an output for each reclassification. Then we can close this one and we can run this script, number 4. Then go here. We can close this one here at the moment, number 4. Double click to open. And then again, we have to add here the 10 original rasters. In this case, is the simulations of the original scale. Then we can click here and add these rasters. I'm going to pass the video faster. In this case, the guide level is going to be the same, 1000. And also we are going to save this file here in the folder of rasters. Is this folder over here, and it's going to be summation rasters number 2. Save. And what we are going to do with this script is to load all the original rasters, then reclassify them with 2 values for the pixel, 0 and 1. Then sum all of them and provide a final raster that is the summation of all reclassified rasters. It's going to be the same as this one, but it's going to be the process totally automatic with the R script. Then run. Now we can close this one. Is this raster over here? As you can see, it goes from 0 to 10, and we are going to do the same as we did with this one, just to compare both of them. Then go here, go to Properties, Single Bulk Pseudo Color. Then we are going to add here equal intervals for 11 classes. From 0 to 10, this color we want to be red. Okay, and this color, what we want is to be transparent. Okay, then apply, and okay. And now if we compare this raster that was created with the new script with the raster that we created with the raster calculator, we are going to see that both has the same results. You can see this one is the one that we calculated with the raster calculator, and now we put on the top the one that we created with the R script, and the results are totally the same. But this one, with this one, we did all the process automatically. But with this one, we did manually. And with this one, with the R script, we can save a lot of time. Remember that you can download all the scripts at the Geo RGB community website at gscourse.online. Then go to the Conditional Gaussian Simulation for environmental projects, click on the course, then get enrolled in the course, start learning, and here you are going to have access to all the lessons. I didn't load the lesson number 5, but we can use as example the lesson number 4. Here at the bottom, you can have exercise file where you can download all the scripts that we are using during the lessons. Also, you can follow us at the Geo RGB YouTube channel. Here you have all the lessons loaded, but there are some restrictions. Well, thank you very much for watching this video and see you on the next lesson.